Hello everyone. Last time we have finished the state till state 8. Now we'll continue from state 8. So state 8 is the exit of the reheater. So we'll do the same analysis as the combustion chamber, and we'll write the first law for the reheater and find the property at 8. So this one is our reheater. We have enthalpy at 7. We have the fuel ratio, fuel of reheater with its HC, and then here we have the mass flow rate of the air plus mass flow rate of the combustion chamber. We have two mass flow rates, one as well as one mass flow rate for the combustion, and at the exit you will have sum of them: mass flow rate of air plus mass flow rate of the combustion chamber plus mass flow rate of the reheater, and this one is enthalpy at 8. This is state 8 and this one is state 7. So we are doing analysis per unit kg of air. Therefore we should divide each term by m dot of air. So if you divide each term, therefore divide by m dot of air. So if you divide it, you will have 1 here. So 1 plus this one will be 1 by AF of Cc into enthalpy at 7 plus that this one is again 1 by AF of reheater into HC will be equal to this one again 1 plus 1 by AF of Cc plus 1 by AF of reheater into enthalpy at 8. As we have said, the enthalpies here and the 7 and 8 are assumed to be enthalpy of air. So enthalpy of air. Everywhere we assume that it is enthalpy of air, and the air is an ideal gas. Let's go back to here. So let's write the energy equation. So 1 by 1 divided by AF of combustion chamber into enthalpy at 7 plus 1 by AF of heating into HC will be equal to 1 plus 1 by F of reheater plus 1 by F of combustion chamber into enthalpy at 8. And for this one we have two unknowns, but the temperature at 8 is known, so therefore I can write H at 8 will be equal to enthalpy of air is T8. Okay, we know the temperature and then we can find unknowns here. Enthalpy of reheater is 183. Again, this is assumed, we will correct it. Good. And let's go back to 9. Again, we will do energy balance for the turbine 2, which is the same as turbine 1. So let's go back to state 9, and I will write here the same energy balance. Eta of turbine 2 will be equal to turbine 2 H9, 8 and 9. This one will be H of 8 and 9. So here I know 8, I know the 8, and I don't know enthalpy at 8 and enthalpy isentropic at 9. So let's find enthalpy at 9. Let's see if we can find temperature at 9. Temperature at 9 and temperature 5 is 65 degrees. So therefore, I can clearly comment of this one. I should find the temperature at 5 because I have not found it. Our only aim is enthalpy. Therefore, we leave the values that we need till we need them. Okay, so temperature at 5 will be temperature of air. H is H5. So I know the temperature at 5. I know the temperature at 9. Therefore, I can find enthalpy at 9. So it will be T is T9. Okay, so let's run it. So we have errors. Okay. By the way, this one is eta 2. So I have written firstly as ISO 2 plus, but I have corrected it eta 2 because it gave error. Names are different. So we have everything till 9. But here I can also find isentropic efficiency of 9. If I find it, I will have excess amount of equations because I can find it. I will show you, and then I can erase one of these two values. Okay, so let's go back to enthalpy, isentropic enthalpy at 9. How can I find it? So for this part, H isentropic 9. So I need entropy of 8 because that is the same as entropy at 9. I need two properties like Gibbs phase rule, and the second is I need pressure at 9. But I know the pressure at 9 because it is the same as pressure at 10, because this is heat exchanger, pressures are constant. So P10 is same as P ambient. This is the same as P1. Therefore, P9 is same as P10, P10 is same as P1, and I know the value of P1, which was the same as P ambient. Okay, so I know this one. So then I can find entropy of 8 because I know the pressure of 8 and the temperature of 8. How do I know pressure of 8? Because the pressure of 8 is the same as pressure of 7, because this one is again heat exchanger and the pressure is to be constant. Okay, let's solve it. So I can find H isentropic 9 will be equal to enthalpy of air. P is P9 and S is S isentropic 9. So P9 is same as P10 and P10 is same as P1. So we have this part, H isentropic 9 is same as S8, and I know that S8 can be found by P8 and T8. So entropy of air, P is P8 and T is T8. Do I know the T8? Let's go back to here. Yes, I know T8, and I only need P8. So P8 will be same as P7 because this is reheater. So, and we assumed P7 here. You see, we assumed it, and let's run it and see our error, because we will have excess amount of equations. You see, this equation resets the value of previously defined variable. So what says that here we are trying to get H isentropic 9, but we have the preset value, which is P7. Okay, but it tries to find P7 that satisfies H isentropic 9 here. Okay, therefore this one resets the equations here. Okay, so what we will do, we will comment this one. P7 is same as P6 by 2. This is assumed before resetting it. So firstly, before clearing this one, firstly I should say that first I should erase this part, because what we will do now is that you should update guess values. Update guess values. Okay, why do we need that? Because till this part we have reasonable guesses. Okay, reasonable guesses. And if I clear this one, or if I clear this one, what will EES do? EES will start to use its guess values as 0. Okay, it will start as 0. But if I update guess values, EES will not start to use its guess values as 0. What we will do, it will start to use guess values as recent values. Recent values, it means that the values that I have assigned for it, for example this one, and the calculations related to these two values. Okay, it will use the recent values with respect to the assumed P7 and AFCC values. Okay, with respect to, because now it will look for the guess values as the recent values with respect to assumed P7 and AFCC values. Okay, this part is a very important part. We should do that. I cleared it. First I comment this one. I will comment all of this, because say this part, I run it, no problem. I update the guess values, update guesses, or Control G, you can use it. If I update it, now EES will find the roots based on these values, on these current values. For any calculation, it will use these current values as its recent guess value. So what will I do now? Now I will clear this one and comment this one. So it says that evaluation, okay, have negative values. Okay, why negative values? For this part, okay, if you go back, so it tries to look for the pressure value that satisfies these equations. But if you go back to variable info, you will see that P P8 and the P7, you see, these are using recent values, but for looking for the next calculation, it uses the values between negative infinity and to positive infinity. What I will do now that I will constrain P8 as 0. Now there will not be any value less than 0 because negative pressure is not here in this cycle, therefore it's not reasonable to put it as negative infinity. Let's press it and run it. So it is, everything is on the way, so everything is okay, it works. Now we have one part implemented. We have cleared this part. Now AFCC, we should find it. So let's go back to next equation. Next equation is that the power of the turbine 2 is given. I will use it now. Go back to our chart. Power of the turbine 2 is given. So how can I find the power of any turbine? It's very simple. This first analysis. So this is turbine 2, and it will have, so the enthalpy at 8 in this mass flow rate and enthalpy at 9. So what we have here, so in is same as out. This is the first law of thermodynamics, and the enthalpy of 8 brings mass flow rate of the reheater, brings mass flow rate of the combustion chamber, it brings mass flow rate of the air. It will be equal to, the turbine gives power as an out. So this is out. So work dot out will be power of turbine 2 or work dot of turbine 2, it doesn't matter. It will be the same mass flow rates, reheater, mass flow rate of the combustion chamber, and mass flow rate of the air. So I will write this equation. This is known. This is known. The mass flow rate of air unknown, mass flow rate of this one is unknown, this one is unknown. So what will I do now? AF of CC is mass flow rate of, we have three unknowns. Three unknowns, one equation. This is the first equation. So AF fuel ratio of combustion chamber will be mass flow rate of air divided by mass flow rate of fuel combustion, mass flow rate of fuel of combustion chamber. This is second equation. And the third equation will be reheater, again mass flow rate of the air, mass flow rate of the reheater. Okay, so we have three equations, three unknowns, and it will be solved. Okay, now it is not excess equation again, so we will need one more equation to solve this problem. So first let's write our turbine 2. It's not an excess amount of equation, so let's write it H8 into mass flow rate of reheater plus mass flow rate of combustion chamber, and that into of air. This one will be equal to same stuff, will be 9. Okay, we should enter the unknowns here. It says two unknowns. Why it says two unknowns? Because we have the equation, but two unknowns are there, because this equation can solve for air or any of it. So let's write it. AF of combustion chamber is m dot of air divided by m dot of combustion chamber. Air fuel ratio of reheater is m dot of air divided by m dot of combustion chamber, reheater. Okay, that's it. We have solved it. Now let's write the values, units for the values, kilograms per second. This one is kilograms per second, and then this one is kilograms per second. Let's go back here. Okay, again we don't have equation to solve for this air to fuel ratio of the combustion chamber, so, but we should find it. So that equation will be, this cycle has two turbines. The first turbine is called the gasifier turbine, this one, gasifier, and this one is power turbine. So power turbine gives power, but gasifier turbine runs compressor 1 and 2. So therefore, the power of, write it here, power of turbine 1 is power of compressor 1 plus power of compressor 2. Let's write it. So for compressor 1, if you do the first law analysis, you will have m dot of air enthalpy of 1, m dot of air enthalpy 2, m dot air enthalpy 3, m dot air enthalpy 4. But for gas-fired turbine, you have m dot air plus m dot fuel of combustion chamber into H6. You will have m dot air plus m dot fuel combustion chamber H7. If I write it, you will have m dot of air plus m dot of fuel combustion chamber into H6 minus H7, H6 minus H7. This one will be equal to m dot of air for the air into H2 minus H1 plus m dot air H4 minus H3. H4 minus H3. If I divide each term by mass flow rate of the air, you can divide or you cannot divide because we know these values. Okay, let's do it as it is. Or you can divide by mass flow rate of air and do it by unit mass analysis. It's not a problem. Okay, let's do that now. Let's write it in EES. We will have the excess equation. It is excess equation because we know the enthalpies, we know mass flow rates, and therefore it will be an excess amount of equation. Okay, therefore we now can clear the we can comment this one out and then solve the problem. Okay, let's solve it. So m dot of H6 minus H7 is equal to m dot of here H2 minus H1 plus m dot of here into H4 minus H. We have, let's see if everything is alright. So, okay, now let's run it. So to see we have the, so first before running it, firstly, okay, let's run it to see how the, yes, we have the excess amount of equations. Okay, now what will I do? I will do the same stuff. First to comment this one, run without this equation, okay, and then update the gas values because I want EES to use the values that I have now. Okay, so if it is okay, then I can comment this one and clear comments of that one. Okay, so we have the values here and it is solved. We don't have any assumed value. Now let's go back to Regenerator and find the values for Regenerator and finish the problem. So again, first law analysis for the Regenerator. Solve it. So for Regenerator, this is again heat exchanger. So we have 9, we have enthalpy 10, you have enthalpy 4, you have enthalpy 5. Okay. Let's write the first law. First law means that in is same as out. What is into the system? In is H4 into here, H4 into m dot of air only. But for the next in 9, we have m dot air, m dot fuel of combustion chamber, m dot fuel of reheating chamber. Out is the same mass flow rates, but now enthalpy 10, and 5 is the same m dot of air. Let's write it. M dot air H4, that is in, plus the next in, m dot air plus m dot fuel reheater plus m dot fuel combustion chamber into H9 will be equal to out. M dot air enthalpy 5 plus m dot same m dot air plus m dot fuel reheater chamber plus m dot fuel combustion chamber into enthalpy at 10. And this is the first law for the Regenerator. solve it. If I solve it, I will get the value of, so I know H4, I know H5, I know H10, and I will find I know H9, I will find H10. So let's write it m dot of air into H4 plus m dot of air plus and base 1 into H9, I will do m dot of some stuff, so it will be 5, and this one will be 10. So, and I have the value for 10. I have solved the problem and all of the enthalpy values are found, so it means that the problem is solved. So for any cycle, if you have the enthalpy values, it has been solved. So let's see what the question asks. So find efficiency of the cycle, we will find it. Air to fuel ratio of the combustion chamber, we have found it. Reheater, we have found it. Mass flow rate of air, it is okay, we have found it. Effectiveness of the recuperator, now we will find it. And check whether energy is conserved or not, we will check it. And then efficiency of the cycle. Yeah, so first let's find effectiveness of the recuperator. Effectiveness of recuperator. Effectiveness of the recuperator means that, so if you go back to this part, regenerator part, so effectiveness means that, so you will have H5 minus H4, okay, that is what you gain from regenerator. Okay, let's draw in another chart here. So H5 minus H4 is what? Real one, real gain from regenerator or recuperator. Regenerator, this is the real gain. But ideal would be, if it is ideal from regenerator, ideal would be that H4 is the same stuff, but H5 leaves the system at the temperature of the 9. Okay, so it means that enthalpy of air T is T9, because this is the maximum that can the regenerator give to the medium, okay, working fluid. Therefore, this will be the ideal, and this is the real, and the ratio will be the effectiveness of the recuperator. Let's write it. So epsilon of the recuperator. The recuperator will be equal to enthalpy ideal, let's say 5, or let's put that as here, enthalpy of air T is T. No, this one will be the downstairs. First upstairs, H5 minus H4 divided by enthalpy of air T is T9 minus H4. See what we have here. So T is T9, brackets of this one, and H4, and it, so it's almost 91%. Good. Okay. And then we have finished this part. Whether energy is conserved for the cycle or not. Let's see that one too. If it is okay, if energy is conserved, then we'll find the efficiency. Okay. Need more slide. Let's put so energy conserved for the cycle means if you will do first law analysis for overall cycle, and you could say that if it's energy conserved, total in for the cycle should be same as total out. Okay, and then we should first write what is into the system. So this is our system. Okay, So we have in as this one, m dot of air into enthalpy 1. We have out, which is q dot out, because here you lose the temperature. T2 is less than T3 and you are giving off heat. Therefore, this one will be m dot of air into H2 minus H3. This is out. Then turbine 1 has the same work as turbine compressor 1 and 2, therefore this doesn't leave the boundary of the system. This one leaves the boundary of the system. You have here work dot of turbine 2 or power 2, power of 2, and here you will have m dot of air into H10. There is no out here because this one is out and this one is in. This one gains and this one leaves, therefore there is no anything here. And as well as we have combustion chamber into the system, this is q dot in, and this one is reheater, combustion of the reheater. So this one will be m dot fuel of combustion chamber into HC, and this one will be m dot fuel of the reheater chamber into HC, because that is what we are gaining as an in. So these are the in quantities: one in, second in, and we have third in. And now let's write the out quantities. This one is out 1, this one is out 2, and this one is out 3. If you write it, it will be m dot H1, this one is air, plus m dot in of fuel of combustion chamber into HC, m dot of fuel of the reheater chamber into HC. That one will be equal to power of turbine 2 plus this one, m dot of air into H2 minus H3 into plus. Here you have this, sorry, this one is not mass flow rate of air only, this is mass flow rate of air plus mass flow rate of the fuel of the combustion chamber plus mass flow rate of the fuel of the reheater, because 3 mass flow rates are there: m dot of the air plus m dot of the fuel reheater, m dot of the fuel combustion chamber into H10. Okay, let's see if it is equal, then we have no problem. If it is not equal, then we will have problem. So another problem here is that we will have excess amount of equation because all of the values are here known. So therefore, I will add here an error function. Error means that if it is 0, then it is conserved. If it is not, it is not conserved. Let's do that and finish this part. We will have check for so error plus here into enthalpy 1 plus if you say the names are okay, m dot of air, m dot of fuel, this one should be okay. Fuel reheater, air, it's okay. Again, it's false. This is false. Okay, let's see. Okay, we have in error, of course, name HC, fuel reheater, steam chamber, power 2. Let's run it, see the error. Error m dot fuel reheater, one of these unknown. M dot fuel reheater, air, m dot air, this one, okay. And it's error is negative 3.09 kilojoules per second. Yes, so we have here small error that I didn't add in for fuel error is okay, so error has decreased, no problem. So this one was the error that I have not added. So I'll go back to slides for the regenerator part. It's okay, so I have not added this part. Good. So now let's run it again. So we have the error which is 0.00004. So that's okay. So that means that energy is conserved. No problem. Okay. This is the first load. We have technically this error can be much less than this one, but here I have put my numbers, therefore there can be error with my numbers as well as errors accuracy degree. Okay, so good. Anyway, this is okay. So value is also very small, therefore energy is conserved. So now let's go back to it says that find efficiency of the cycle. So let's find the efficiency of the cycle and then plot the TS diagram. Cycle to be, so cycle is eta cycle is work dot net out divided by Q dot in. So let's solve it for now. So here we will have work dot net out is only by power turbine, so net out, and the Q dot in is the in by reheater and the combustion chamber. Power turbine 2 divided by m dot fuel reheater into HC plus m dot fuel combustion chamber into HC. Okay, let's solve it and find eta of the cycle. Eta cycle is equal to E2 divided by m dot of reheater into HC plus m dot of fuel combustion chamber into HC. Now the efficiency is, where's that? 58%. That's good. It's good, and the more realistic. But we have finished the questions, and the only part is okay. So we have finished the questions, and the only part is left is TS diagram. Okay, so firstly let's draw the TS diagram. Firstly a real cycle, then I will do the ideal one without intercooler and reheater, not ideal. So not TS diagram. So let's on it. We have all of the T's. So we have T1, T3, 2E's, 4, 7, and 10. These are not known. Let's find 2, 4, 7, 9, 10. Let's do is temperature at here. H is H2 because H and the T are directly proportional. So let's find it. And for ideal gas, enthalpy is only a function of the temperature. So T2 is there, 4, 7, 10. 4, 3, 7, 3, 10. P that 7, 3, 4, 7, 10. Okay, temperature. Let's see entropy. For entropy values, I need 2, 4, 5, 7, 10, 9. S2, S4, S5, S7, C, 4, 5, 7, 9, 10, S9, S10. That I will go for 1 and copy and paste it. Here T is T2, T is P2. That. Okay, let's change it to 3, 4, 5, 7, 9, 10. Let's go back here. 4, 5, 7, 9, So the T and S values, not plotting. Plot it, we'll need plot, new plot window, XY plot. X plot will be S, Y plot will be temperature. And I don't need a logarithm, I need grid lines, I need array indices show me because I need to know which one is which, T1, T2, T3. And also I don't need line, I need symbols, and color red is okay. Good. Plot it. Okay. These are the temperature values and these are the entropy values. Okay, so what I will do now, so you can draw it here, so you can take a line, and take a line, and for example, go from 1 to 2, okay, then 3 to 4, etc. I will do in PowerPoint, so I copy and paste it. Here, here, and then copy and paste it. See, and let's go to PowerPointing. For the next slide, I will add this TS diagram and work on it. TS. Okay, so firstly 1 to 2. Where is that? I should go to diagram window here and add it. This is the cycle that we have. Okay, everything is good now. Good. Okay, so I will go to PowerPoint now. Got it. So firstly, from 1 to 2. From 1 to 2, yes. From 1 to 2, it is real, therefore entropy will increase and the temperature will increase because this one is the compressor. So therefore you will have the temperature increase as well as entropy increase. You can see here. It is not exact profile, but it is good. From 2 to 3, temperature should drop because it's cooler, but entropy should also decrease. So let's go back. Good. 3 to 4, same as 1 to 2. Good. And now comes 4 to 5. Here we will have increase in temperature, therefore increase in entropy. Good. So these are a bit curved. It's not possible to do it exactly. 5 to 6, temperature will increase and entropy increase also. You'll have a curved line, something like this. Okay. 6 to 7, entropy will decrease because temperature drops in turbine, power pressure drops because you get the power, and entropy should drop 6 to 7. Drops very little. Good. 7 to 8, then again you will have dropping temperature. And here dropping temperature as well as entropy. Okay. And 9 to 10 you will have dropping temperature, dropping entropy. Okay, so this line can be connected, but in our case it's not important, but you can connect this. Okay, this is the TS diagram. So the next part of the question says, there was no so plot TS diagram if we want to use intercooler or reheater. So you can do that if there is no intercooler, this part, and if there is no reheater, this one. So this is the famous one in any book. You can find in any book, so I will not do that part because this one is very easy. Okay, so the problem is this one, and we have finished. Okay, thank you, best wishes.